Hello. Right. Um, Dear members and distinguished guests, my name is Patrapon. I am a member of SPE Young Professional and here to help running the meetings and support the section with Kun Kasian and Kun Surachai. And I will be the program facilitator for tonight. On behalf of the SPE Thailand Board of Directors, I would like to welcome you to SPE Thailand monthly technical meeting this month for the month of October. This month, we have received the support from SPE International with the distinguished lecturer from the UK. Thank you for being here tonight, and we are happy to see many smiling faces supporting our events. Also, a special welcome to our students. Please raise your hand to show us where you are. Right. Thank you very much for joining us. Right. Apology for some technical issues. So before we before we continue with our program, please take a note of the safety announcement. There are no emergency drills planned for tonight. So in case the alarms goes off, please remain calm and follow the exit sign towards the designated area marked by the hotel. So here is our agenda. I will highlight some of our activities. The program chair will introduce the speaker. Then we will have our presentation, followed by some Q&A and closing remarks before the lucky draw. Hello. Right. So all the programs shall be concluded just before 7:30. Right, next is section announcement. So established in 1980s as a non-profit organization, SPE Thailand proudly represents just south of 1,000 professional and students members from diverse disciplines across the upstream petroleum industry. Our mission is to promote technical knowledge sharing, professional development, and community building to ensure a sustainable future for the exploration and production in Thailand. We actively organize technical meetings and social events that encourage networking and exchanging of technical ideas to keep our industry community active. Right. SPE Thailand has just celebrated its 45th anniversary together with the season opening last month. And I hope you were able to attend to celebrate our milestone achievement together. And for those who were not there, you may watch the recordings of the whole event on YouTube, SPE Thailand channel. These companies are the sponsors who support us, our monthly technical meeting program for the season 2025 and 2026. For any of you who may have just joined this meeting, if you would like to see your company name up here, please reach out to us. And the season has just begun, and we have many months left to have your company logo present to the community. So we appreciate your support, and of course, our society needs you. Thailand section, valid memberships. As this month is indeed a very lucky number of 999. Thank you all. This is a combining between 469 professionals and 530 students members from Chulalongkorn, Suranari, Prince of Songkhla, and Chiang Mai university student chapters. However, we still have just over 200 professional members from 2024 who has yet to renew the membership. Please recheck your membership status. And if labs, please consider to renew it. So all apps, please invite a colleague to join our meetings, and even better to join SPE, because we are always happy to see new members. Let me remind you that SPE Thailand is still one of the largest professional oil and gas industry organization where you can regularly engage in professional venue but relaxed environment. And there are plenty of reasons why you should maintain a valid membership status, and even more reason to join. I'll not go through all of them, as you can see on the screen. But worth mentioning that key benefits of belonging to one of the most active SPE section in the Asia Pacific are the regular opportunities to network and share the knowledge and socialize with peers and of the same interest in this industry. Right, ladies and gentlemen, we will now move on with main presentation. Can we have, please have Khun Surachai, SPE Program Chairperson, up front to introduce our speaker.
Hello. Good evening, everyone. My name is Surachai. I'm the one of the board committee of the SPE under the program chair. It's my honor tonight that have the chance to introduce our speaker today. Michael is an experienced industrial professional and leader with over 35 years experience. A graduate of the University College Dublin, and Michael served as the API committee which developed the procedures for return permeability testing. He has authored many technical publications on the formation damage and the numerical well modeling, have developed the procedure for modeling flow in wells and reservoirs using a computation fluid dynamics. Michael served as an SPE Distinguished Lecturer in 2009 to 2010, and again in 2014 to 2015, and has presented technical papers and training courses globally. More recently, Michael has worked in the CO2 storage and has contributed to well design in several CO2 stores. So it's time that please welcome Michael for the presentation today.
Okay, thank you very much for the introduction, for the invitation to come and speak here, and to thank you to all of you for coming out this evening to hear what I have to say about carbon capture and storage wells. This presentation that I'll deliver this evening is part of the SPE Distinguished Lecturer Programme, and that program is funded by the SPE Foundation, Offshore Europe, and AIME. So I'd like to thank and acknowledge all of those for helping me to travel and to meet with so many different people in the last 2 weeks. This is my 7th lecture in the last 2 weeks. So I've had an interesting journey through New Zealand, Australia, and now into Thailand. I think I can confirm that of the 7 lectures or presentations that I've given, this is actually the highest attendance. And one of your colleagues seems to be very keen that you've beaten Perth and you've beaten Brisbane. So you can take credit for that. So I'd like to talk to you this evening about carbon capture wells and try to explain to you what I think is the same about those wells. So in other words, the same as oil and gas production wells and the same as water injection wells that many of us have worked with for a long time, but also what is different. So to give my perspective on moving into working in carbon capture wells from a number of years in oil and gas, as to what we can use from our existing experience, but also what we have to learn and what is a little bit different about these challenging wells. My formal name is Michael Byrne, but I sometimes think that the only people that call me Michael are my mother and the SPE. So when I hear Michael, it triggers some kind of childish response that I must be in trouble. So if we're talking later, I would much prefer that you use Mike, which is my much more familiar name when you talk to me. I work for a company called Elemental Energies. I joined Elemental Energies 8.5 weeks ago. So I'm very new to them. They're new to me, but I'm very grateful that they agreed that I could travel on an SPE Distinguished Lecturer Tour after only 6 weeks working with them. I did tell them before I joined, but I'm still very grateful that they've allowed me to travel. So what I'd like to do today is really give a very high-level introduction to carbon capture and storage. For those of you that are not familiar with the topic, just to give you some sense of what we're talking about when we talk about wells for carbon capture and storage. I'll talk about what's the same and what's different in CCS wells. I'll talk about the two different types of store or reservoir that we do currently and are planning to inject or dispose of CO2 in. And those two different types are saline aquifers and depleted hydrocarbons. Most CCS developments worldwide are either one or the other. There are a few that you could argue cross the boundary, but really we're dealing with either saline aquifer or we're dealing with depleted hydrocarbon. And so I'll talk about each of those types of store and the wells into those stores and the specific challenges in a little bit more detail. I'll talk, because it's where I come from, about laboratory testing and about modeling and what we can do in order to try to solve some of these new challenges that we have in these different types of wells. And then, of course, I'll conclude and acknowledge. So what is CCUS? Well, carbon capture, utilization, and storage is the removal of CO2 either from emitted gas or directly from the atmosphere, the utilization of that CO2, so for example in enhanced oil recovery, and the storage in subsurface reservoirs or what we call stores. But essentially these are very similar to the reservoirs that we've dealt with in oil and gas for many years, and sometimes they're exactly the same because we're just putting CO2 back in. This presentation won't talk about capture or utilization. I'm just going to talk about storage and the wells that we put into those different types of stores and the challenges with those wells. So I'm focusing exclusively on storage in the two different types of stores. Oh, sorry, it has gone. So the first question. I said that there were a lot of things that were the same about these wells, the same as we're used to in oil and gas and water injection. So what's the same? Well, the purpose of the wells, the broad purpose or reason for those wells is the same. They are to connect the surface to the subsurface. That's what the wells are for. They're to allow efficient communication between the surface and the subsurface. That's what any well that we design and implement is for. And so that's exactly the same for carbon capture and storage as it has been for oil and gas production wells and water injection wells. And of course, we need to consider safety, we need to consider well integrity, we need to consider the upper completion, the lower completion, and the sand face design. Again, that's the same as we're used to. There's nothing different there. We need a multidisciplinary approach. And if I've seen any change in our industry in my 35 plus years in oil and gas, it is that we have become better at multidisciplinary approaches. There is less of a siloed mentality now where drilling drill the wells, completion complete the wells, and production produce the wells. That integrated multidisciplinary approach across subsurface, across production technology, production engineering, completion engineering, through to drilling and completions departments, that is much more effective as a multidisciplinary approach, and it is absolutely required in carbon capture and storage wells. The wells that we're going to put into these stores, just like the wells that we put into oil and gas reservoirs, are expensive. There is no denying that. So they are expensive, but they are absolutely critical. We have nothing without wells. If we don't connect the surface to the subsurface through efficient, good communicating wells, we have nothing. We don't have a development. So that's exactly the same as for oil and gas. And the operating or injecting time, the time that we're going to be injecting CO2 for, is broadly similar to the time span that we design oil and gas wells for. It's maybe 5 to 50 years. So it depends on the well, it depends on the reservoir or the store, but 5 to 50 years is typical design life. So the injection lifetime of those wells is pretty similar to what we're used to. So lots of stuff that's the same when it comes to carbon capture wells. And that's probably a good thing. If you're moving from oil and gas into carbon capture and storage, we have a lot of knowledge. But there are some things that are different. So, starting point, CO2 is different. CO2 is unlike oil and gas and water. It has very interesting, challenging behavior that we need to understand when we're designing wells. We need to understand what the differences are going to be. We need to understand temperature. We need to understand the phase behavior. And this is a relatively simple, a relatively simple phase diagram here showing the phases of CO2. Now I say relatively simple because when we deal with CO2, we have to deal with enthalpy rather than just simple phase behavior. But for simplicity in a short lecture, I'll just leave it at this. But we need to understand where we are in this phase diagram with the different types of stores that we're dealing with, and therefore the wells into those stores. And it's really important that we understand that fully, and perhaps more so than when we're dealing with just water injection, where we're essentially dealing with single phase all the time. Here we're dealing potentially with multiple phases during the injection process in the wells and in the store. It's complicated. The rates and velocities at which we're injecting CO2 in many of the high-profile projects around the world are a little bit different from what we're used to in conventional oil and gas. And particularly for depleted hydrocarbon stores, and I'll come back to this, we may be injecting at significantly higher velocities in the well and in the near wellbore than we do, or than we're used to in conventional, even high-rate gas wells. I'll explain why that is a little bit later. Corrosion can be a challenge, and it can be a big challenge when we're injecting CO2 and we have fluids in the reservoir, such as brine or water. We mix CO2 and water, and there is a high corrosion risk. And so we need to pay special attention to corrosion. We may want to employ forms of flow control, such as downhole choking, as we inject the CO2 in order to manage the phase behavior of that fluid within the wellbore. And that's not something that we're used to dealing with in oil and gas. We don't talk about choking downhole when we're injecting water. In fact, it's usually the last thing we would want to do. And that's a bit different when it comes to carbon capture wells. And I said that the injection lifetime is broadly similar, but we need to plan for long-term well integrity and security, really long-term. So thousands of years of well integrity. We inject CO2 in order to dispose of it, and I'm not going to get into the debate of whether we're saving the world or not, but if we're trying to save the world by injecting CO2, and that CO2 leaks out after 100 years, then we haven't done a very good job. So we need to ensure long-term well integrity. You might argue that we should be doing this for oil and gas wells as well, so that they don't leak, but there is an added incentive when it comes to a disposal well, where we're trying to keep as much of that CO2 away from the atmosphere as we can. So that long-term well integrity is a little bit different. So getting into the detail of these two different types of stores, I'll deal with saline aquifers first. Well, saline aquifers are basically just big reservoirs filled with water at usually significant depth in the subsurface. Because they're already filled with water, they're often at hydrostatic or normal pressure, and therefore any CO2 that we introduce to those stores is going to increase the pressure in the store. So we're going to go probably above hydrostatic. What we need to ensure is that we can do that without compromising the seal on that store or reservoir. And for that reason, we need these things to be pretty big. We need them to have great lateral extent. And so when we're talking about a well and an injection well, the reach of that injection well, which is permeability dependent, can be quite significant. It can be several kilometers, which is not necessarily what we're normally talking about when we design a water injection well. So again, that brings us some challenging design criteria when it comes to the well design. The CO2 plume in a saline aquifer is gravity dependent. CO2, regardless of the phase that it exists in, so whether it's liquid, dense phase, or gas, it will have a lower density than water. What that means is that the CO2 will tend to rise to the ceiling of that store. And that's important because we're trying to manage the placement of that CO2 into the store, and it might again lead us to change our well design, for example, to inject more towards the base of the store to give us a greater volume of injection as the CO2 migrates up towards the ceiling. So there are some interesting design challenges when it comes to saline aquifers. We also need to think about the lower completion selection and salt precipitation and corrosion, and I'll deal with each of those in a little bit more detail. So what about the lower completion? Well, you might think, well, these are just disposal wells. We're trying to get rid of as much CO2 as possible. Do we not just keep it really simple? Case, perforate, inject CO2. Well, that might work for some stores, and I'm sure it will, and does work for some stores. However, we need to treat these wells as we do with water injection wells for the potential that sand may come back into the well with time. With shut-in of the well, we may have cross-flow, where we have higher pressure in one part of the well than another, and that pressure equalizes through the well, potentially filling the well with sand. Or we may have a liquid hammer effect. So when we stop injecting CO2, we may have that pressure wave that can draw sand back into the well. So for those reasons, we may want to deploy sand control, sand screens, potentially gravel packs in these CO2 injectors. And to those of you working in oil and gas, you'll probably be thinking that introduces a bit of complexity. It introduces a little bit more challenging in terms of the fluids that we can use, how we use those fluids, and how we get rid of those fluids if we need to before we start injecting CO2. Ideally, we would like to flow back these wells. We would like to produce them before we inject. But when we complete with sand control, we really would like to flow back because we have a residual mud cake, regardless of how we've completed the well, or regardless of whether it's standalone screens or open hole gravel pack, we will undoubtedly have something in the well that normally we would want to flow back. And so we need to understand what's going to happen when we drill these wells, and if we don't flow back, we chase drilling mud, completion fluid into the formation with CO2. So we need to understand those interactions, which will be different from what we're used to in conventional wells. For saline aquifers in particular, salt precipitation is a risk. We're injecting CO2, which is essentially a solvent, into a water-saturated near wellbore. We will undoubtedly dry out the near wellbore to some extent, precipitating salt. Now, that is a challenge. If we precipitate salt in the near wellbore, will that affect our injectivity? There's no simple answer to that, but it's something that we have to try to understand. The salinity, of course, is very important. If we've got very high salinity, then the salt risk is higher. In saline aquifers, we have quite an abundant supply of water and therefore potentially salt, and we may have recirculation of water through the store. If we're just injecting at the top, we might have water coming back into the wellbore or back into the near wellbore, and a fresh supply of potential salt. So this salted region in the near wellbore is definitely a challenge, particularly early on in a development. The long and well-established Sleipner CO2 disposal project in Norway, which has been running for at least 20 years, had significant salt problems early on, and they had to water wash their wells frequently early in the development. Once they'd kind of overcome their initial salting problems and essentially pushed most of the brine away from the wellbore, then the problem disappeared. So it is something that we need to be aware of in order to preserve our injectivity. It can also be a challenge in depleted gas reservoirs where we have a residual water in the near wellbore. We might have 30 or 40% water, and now we're injecting CO2, potentially gas phase CO2. We will undoubtedly precipitate some salt. If we only have 34 or 40% water saturation, though, it's unlikely that we're going to significantly affect the injectivity, even if we precipitate all the salt from all of the water in the near wellbore. So it's more of a challenge for saline aquifers than it is for depleted hydrocarbon. Another risk, and not exclusive to saline aquifers, and not exclusive to CO2 injection wells, is corrosion. So pure CO2, so where we have pure CO2 and where we're injecting only CO2, there's only CO2 in contact with the wellbore and with the near wellbore, then corrosion is not a risk. CO2 on its own is not corrosive. However, when we mix CO2 with water, we have the potential to generate carbonic acid, and carbonic acid is corrosive. And for that reason, we may have to deploy corrosion-resistant materials anywhere that there's a risk of CO2 and brine being present together, either during injection or during shut-in periods. And the shut-in periods here are critical. You might like to think that you can design CO2 injection wells to always be on injection and never shut them in. We know from our experience in the oil and gas world with water injection wells that that is not a practical aspiration. We will have to shut in these wells from time to time. And there are projects where delivery is by intermittent supply, by trucks or by ships, where we're designing in shut-in periods. And we'll actually be injecting for less time than we're shut in. All of that means that when we shut in the well, we need to understand if there's a risk of brine flow back into the well, and if there's a risk of convection currents developing within the well immediately after shut-in that could carry brine or wet CO2 higher up into the well. So we might have protected the lower completion with high-grade alloys, but what about higher up in the well? And this little animation here is showing some convection with computational fluid dynamics modeling, but it's showing immediately after shut-in that we're drawing up, and there's a lot of energy inside that wellbore that can draw in the well away below the lower completion in a sump or somewhere else. Then we can potentially draw it back up the wellbore, and we then need to start thinking about corrosion higher up in the completion. And corrosion, high-grade alloys, we're talking cost. And so this is a very important cost consideration in some developments, particularly in saline aquifers. You can see that animation has started again, and we have all of this energy, all of these velocity vectors showing the transfer or the convection of fluid up the well once we shut it in. And unfortunately, we're not just dealing with CO2. So most of the CO2 sources will be contaminated. And what I mean is that they won't just be CO2. In many of the cases that I've worked with, we're looking at up to 5% contamination of the CO2, and contamination which is expensive and difficult to remove. So we may have to accept that we will have sulfur oxides, we'll have nitrogen oxides, carbon monoxide, hydrogen sulfide, water, and more in that injection stream. Now, many of these substances simply increase the corrosion risk, because now not only are we potentially going to have carbonic acid, but we can also have sulfuric acid, we can have nitric acid, and these acids will increase the corrosion risk and mean that we have to do something to mitigate. Mitigation, that we could do things like decontamination of the supply. It's three easy words to put on a slide, not so easy in reality to do, so it's important to consider. Material selection, of course, we can go with very high-grade alloys, adding significant cost. So there is something, we really need to understand this properly before we go down this road. And there are some chemistries that we may be able to deploy to try to keep that mixture of CO2 and water away from the wellbore. Deeper into the formation, we're probably okay, but it's in the wellbore that we need to be careful. Okay, so moving to the second type of store, and I said there are two types of store. Those saline aquifers, I've dealt with some of the challenges there. Depleted hydrocarbons are in many ways quite different. So these are reservoirs that we've produced usually for quite a long time, removed most of the mobile oil, or predominantly here we're talking about gas reservoirs, that we have removed a lot of the gas, and that makes them almost ideal stores, because we know one thing, that they've sealed that hydrocarbon for millions of years, so we know that they are robust. They're essentially empty. We've taken out a lot of pressure, we've taken out a lot of fluid, and we potentially then have a very simple solution to disposing of significant volumes of CO2. And of course, there are many of these stores being developed at the moment. In these stores, though, some of them are so depleted that it's really difficult to drill new wells, because we've depleted down to such low pressures. I've worked on stores or potential stores where we're down below 100 psi. And now we're talking about drilling and completing into something that has only 100 psi. So at the very least, we're going to be at significant overbalance when we drill and complete. And in the worst cases, we can't reasonably drill and complete when the store pressure is so low. So there are some considerations we have to have there. it's highly unlikely that when we do drill new wells into these stores that we can flow them back to clean them up, which is something we would like to do. We obviously do it for production wells, but even for water injection wells, we'd quite like to flow them back. It's the same here. We'd quite like to flow back, but we've got no pressure. So how can we flow them back? We can't clean them up in the way we might clean up a conventional well. There is often significant cooling associated with the injection of CO2 as we go from a higher pressure supply to a low pressure store. Then significant Joule-Thomson cooling can lead to very low pressures in the well and at the sand face. Or sorry, low temperatures in the well and at the sand face. What temperature are we talking? In some of the projects I've looked at, we're talking maybe -20, -30 degrees C in the lower completion and into the near wellbore. That's pretty low temperature for our industry. If we think of our industry as oil and gas, we're not really used to dealing with things at those kind of temperatures in the wellbore, downhole. And so we need to think about where that happens and when it happens. We also may be at extremely high rates, or high velocity, I should say, in the near wellbore. We're looking in some of these stores, or in individual wells, at maybe rates of 4 million tons per annum. Those of you involved in carbon capture might mean something to you. Those of you not involved will say, what's he talking about, 4 million tons per annum? I don't know what that means. 4 million tons per annum is roughly equivalent to 200 million standard cubic feet per day in gas production terms. So pretty high rate. Our friends in Perth, where I was until yesterday, will say 200 million is nothing. We've got 400 million in some of our wells, but it's 200 million is still a pretty high rate. So we're used to that rate, but what we're not used to is less than 100 psi of store or reservoir pressure. And what does that mean? Well, what it means is very high velocity. If we have a combination of high rate, low pressure, that leads to high velocity, and I'll come back to that with a couple of examples. One of the options for depleted hydrocarbon stores that are at very low pressure is, well, we've got all these wells that we've been producing from. Could some of them be turned around and used as injectors? So these, what are often called legacy production wells, although I worked on a project in Spain recently where the operator liked to call these wells not legacy, but vintage wells. And I'm leading a campaign to change the name legacy to vintage, because I think it sounds better. But anyway, these wells that have been there for a long time in these stores, could we not just use them as injectors? And one of the good things is that that's relatively low cost. We don't have to drill them again. We may not even need to complete them again if the completion interval is appropriate for CO2 injection. So that's a pretty good thing. That overcomes the challenges that we face where we might not be able to drill new wells. So let's get some pressure in there through these vintage wells, and then we can drill new wells potentially for higher rate injection. They've also effectively been cleaned up for a long time, maybe been producing for 30 or 40 years. The near wellbore in those wells, in my opinion, will often be pretty well cleaned up. So they seem like ideal candidates. However, we have to consider that a good producer doesn't always equal a good injector. There are a number of reasons, and we've experienced this in the oil and gas industry where we turn producers into water injectors and we get very poor injectivity. There can be a number of reasons why that happens, and we need to be careful that we don't just make that assumption that it's been producing, it must be a good injector. One of the things that can happen is that we can have residual damage that doesn't affect flow in the production direction. And I've tried to show this here. I'm sorry to those of you looking on at other screens, you won't be able to see the pointer. But what I'm pointing to here is the sand face, where we have some residual damage, residual mud cake, for example, on the sand face. On the screens here, and this is a screened completion, so a sand control completion, we also have a little bit of residual completion damage, but there are flow paths with no resistance to flow. So we can flow out through here, into base pipe holes and out. So there's something there, but it's not affecting production. And I believe that many, many of our wells that seem to produce with no issues are in this state. And that's fine until we turn them into injectors. And we start trying to inject. We inject down here, and what we do is we redistribute some of this material, residual mud cake that was on the screens. It goes back onto the formation face. And now we have a complete seal on the face that we want to inject through. And that might lead us into a situation where we have to, early on, create or develop some non-matrix injection. That's the politically correct term. Anybody want to say what non-matrix injection is? Yeah, you said it first. That's good. It's not, this is being recorded, so there is a reluctance to talk about fracturing in CO2 injection wells, just like there is in water injection wells. Probably 90% of water injection wells inject under some form of fracturing at some stage in their lifetime. It is likely that CO2 injection wells will too. The key is not whether it happens or not, but how safe is that process? How controlled is that process? Do we control within the store, or is there potential for a breakout? And there's a lot of work that has to go on to establish that. It is likely to happen. Now, it's not just caused by formation damage. It may have to happen regardless of formation damage. It may be that the combination of injection rate and rock strength simply can't handle it, and so we do have to have some kind of enhanced permeability in the near wellbore, non-matrix injection or fracturing. So it's important that we realize that, and that we don't try to pretend that it's not going to happen. What we have to do is prove that it will be safe, because again, there's no point in us injecting this CO2 if it's coming back again. So we have to make sure that it stays where we put it. So this is just an illustration of injection, and one of the challenges that is not unique to CO2 injection, but this is a simulation of a well here. This very thin little needle here is the well injecting into a store. And what you may not have seen the first time it ran, but hopefully you'll see it the second time it runs, is that when we start injection, the pressure builds up quite significantly in the heel or at the top of this well. And that injection pressure that's building up is a strong heel to toe effect. And if we start injecting, if this is a saline aquifer, for example, we start injecting here at high pressure, CO2 starts to fill here. There is no motivation for the CO2 that's following to travel and inject here, where there's brine in the near wellbore, because there are relative permeability effects to overcome. So the CO2 will exclusively travel out along the ceiling. And this means that we have to think about our injection wells. We think about where the flow is going to go. I suppose there's a mantra here that is for all wells, whether they're CO2 injection wells or not. Fluids will go where they want to go, not where we want them to go. So when we design the wells, we have to bear that in mind. We might say, oh, we'll complete the entire interval, and fluids will go into the entire interval because that's what we want. When we start injecting, or when we start producing for that matter in production wells, that's not always what happens. The fluids will go where they want to go. They'll follow the path of least resistance, and that is not necessarily for the entire completion. So we need to understand this carefully, and we need to understand this properly for carbon capture wells. I mentioned high velocity at the sand face, and this is a very clear example of high velocity that can develop at the sand face. So in this case, we're looking at a wellbore here. This is a snapshot from a CFD model. We're injecting down the wellbore out into these perforations. Because it's CFD, the perforations are all there, basically. It's not an analytical solution, it's a numerical simulation. And you can see here at the near wellbore, we're starting to see something. If we zoom in, you can see that intensity of color here, and that's velocity. And that equates to about 70 meters per second. 70 meters per second in the lower completion is not something that we're that familiar with in conventional oil and gas wells, even high-rate gas wells. And it's this, let's say, bad combination of high ambition for injection rate and extremely low pressure that we don't have in high-rate gas wells, because they're only high-rate gas wells when we have decent reservoir pressure. So this is something different. And what we're seeing is that there is an increased erosion risk in the lower completion. But I want you to think a little bit about what's happening just out here in the formation, just away from the perforation or just away from the sand face. We also have high velocity. So we can be dealing with velocities that are significantly higher than we've dealt with in the oil and gas industry before. Excuse me. So back in 2009, 2010, I was on a similar tour as a distinguished lecturer, a little less grey, a little less wise perhaps. But as part of that lecture tour, which was mainly dealing with formation damage, I used to throw paper in the air to demonstrate what happens when fines migration happens. It's a damage mechanism that is quite common. And for subsequent years, when I'd go to meetings or I'd go to conferences, people would say, "Oh, you're that paper throwing guy." They wouldn't say, "Oh, you're that world-renowned formation damage expert," or, "Oh, you're that guy who developed advanced numerical modeling for near wellbores." No, you're the guy who throws paper. I'm not that offended, because at least they remembered something about my talk. But I thought it might be interesting to revive that, but with a little bit of a CO2 view on it. So what this demonstration did, and I'm just wondering if I should go to the center of the room, because I have to move away from the mic. So I'm maybe going to go down to the center of the room and use a strong voice. Demonstration really is to show what happens with fines migration, and I want to apply this to carbon capture wells. So if this is kaolinite clay. So you can see that picture up there, or that picture there. That is kaolinite clay, and it looks like the pages of a booklet or a book. So geologists, being clever individuals, I'm a geologist by the way, they call it booklets of kaolinite clay. Thank you for the food. So they talk about it as booklets of kaolinite clay. That sounds pretty obvious. That's what it looks like in the reservoir. If this room that we're in here is the core of a store, so this is a store that we want to dispose of CO2 in. And this entire room is one of the pores in that store. And the door that's open at the back of the room is the entry to this pore. And that picture right up at the end, there, the SEM picture of kaolinite clay, that's the exit from this pore. So that's the pore throat, that the CO2 comes in through the door, out through the pore throat over there. And if this kaolinite clay is sitting attached to the wall of the pore, doing no harm to permeability, doing no harm, not moving, very low volume, very small surface area, the fluid coming through here is not disturbing this at all, and this is not disturbing the fluid. If we're at low flow rate, nothing happens. Low velocity, nothing happens. However, we suddenly decide we want to flow at extremely high velocity through this pore. We want to pump lots and lots of CO2 into the near wellbore very quickly. that may do is disturb or disperse this clay. I'm going to try and show you what that looks like on the scale of this pore that we're in. So if I disperse this clay, look at what happens to it. So it's spread out significantly. We now have quite a big surface area. I'm going to pick some of this up. Take this, and this is flowing with CO2 through the pore, and now we come up to a pore throat. And I can start to cover this pore throat. I can cover the exit to this pore. And if this keeps on happening, eventually we'll reach a situation where that pore throat is blocked. So the CO2 that we're trying to get in through that door, and somebody's just closed the door now, so the demonstration is losing its effect, but that's coming in through that door, coming out through this pore throat, it can't. So what happens next? It goes to the next room, and the next room, and the next room. And this same process happens in all of those rooms. And eventually we get to a situation where we can't flow easily through these pores and pore throats because of fines migration. And we've plugged the pores, the pressure builds up, the injection pressure builds, or the injection rate decreases. And so fines migration in the near wellbore can cause us quite significant problems in conventional oil and gas reservoirs and now in CO2 stores. I'm not saying this is going to happen in all stores. It's very geology, rate, chemistry dependent, but it is something we need to think carefully about, especially with the high velocities that we're considering. Okay. Another particular challenge for depleted hydrocarbon stores, because of the temperatures, the low temperatures that we may be seeing at the sand face and inside the near wellbore, inside the reservoir, are hydrate and ice formation. If we're below 0 degrees C, there is potential that any water in the near wellbore turns to ice. There is also potential that we get CO2 hydrate formation as the CO2 meets the water in the near wellbore. And both of those challenges can lead to permeability decline, to pressure buildup, to injectivity inefficiency. And so we need to understand whether these things are going to happen or not. We need to understand what the salinity of the water is, because that affects the potential, particularly for hydrate formation. One of the good things about ice and hydrate formation, unlike salt precipitation, is that ice and hydrate will melt. So if we stop injection, the temperature rises, the ice and hydrate melt and disappear essentially. So it is something that we could potentially manage through well shut-ins. But of course, I've explained already that well shut-ins may cause us other problems. So again, it's a balance that we have to strike and we have to find. And I won't attempt to explain in detail this complicated diagram. The point is that it's a complex relationship. The relationship between brine, solid salt formation, hydrate formation, ice formation in the near wellbore is temperature and pressure dependent, but it's also chemistry dependent. So we can get hydrates forming here above 0 degrees. But if we have higher salinities, as we move left, we're getting into higher salinities, we need to be down below maybe -12, -13 degrees C for hydrate to form. My point is that we need to understand where we are in this hydrate, ice, and salt risk diagram in order to manage our injectivity and understand it before it hits us. Because many of the wells that we're implementing in these stores are wells that we really don't want to have to try to get back into. So we need to get it right from day one. We don't want to start getting into interventions. And just another, I suppose, challenge with these depleted stores and low temperature is that injecting at low temperature can cause us some very specific problems with the well integrity, and potentially with cycling of temperature as we inject, stop injecting, inject, stop injection, and with that low temperature, here we're looking at minus 15 degrees C, we can cause debonding between the cement and the casing. And this is showing in this particular case with finite element analysis, showing a 200 micron microannulus developing between the casing and the cement. Well, why is that important? Well, that's a leak path. That's a well integrity issue, and the CO2 that we're trying to inject potentially will be traveling back up again in this leak path. So we need to be careful when we're designing these wells, new wells in particular, as to how we use conventional cements? Do we use extreme low temperature cements? There is new technology that has been developed and is still being developed to try to mitigate some of these challenges that we have, particularly with low temperature in depleted hydrocarbon stores. And just to mention downhole choking. So this is actually quite an important topic when it comes to some depleted hydrocarbon stores, where we're trying to control phase behavior at various different rates of injection. And it's not an easy thing to do. But there are downhole chokes being developed, some of them relatively straightforward, but some of them quite complex, with complex controls, complex components that we need to make sure work, because we haven't used this type of equipment before under the conditions that we're going to be operating. And so it's an important area that we need to understand for erosion. We need to go through qualification, and we need to realize that we're dealing with innovation here. And with many of these challenges that I've spoken about, there are tests that can be done. There's laboratory testing, there's screening of fluids, there's mixing of fluids. Many of those tests are just the same as we've been doing for years and years in oil and gas. However, we need to be using CO2. So early on, when we started to look at CO2 injection wells and started doing laboratory tests and things like return permeability, there were laboratories that were testing with nitrogen gas instead of CO2 because it's easier. And to me, that's just a nonsense. We really do need to be testing with the fluids that are going to be there under the conditions that are going to be there in the wellbore in order to understand them properly. But most of the laboratories now, I think globally, have got themselves up to speed to be able to handle CO2 in its various phases, under various different conditions as required. So things like drilling and completion fluid testing, and critical velocity testing, well, that is to look at that paper throwing that I showed you earlier. So if you have core and you can replicate the velocities that you're likely to see in the near wellbore, you can identify if that's going to happen or not. Because in some cases, it's not going to happen. You don't need to worry about it, but you can't tell that just by looking at the rock. You do really need to replicate it to see if it's going to be a challenge. If that's going to be a challenge, then there's not necessarily an easy solution to fines migration. This is something we know from the oil and gas industry. It's not an easy damage mechanism to fix. And of course, with all of this, it's important to upscale the results. If you do laboratory testing or even yard testing, it's really important to put that into perspective and not just assume that the laboratory test, because it's showing 80% damage, is a really bad thing. It's going to kill your development. You need to understand what it means in terms of the well, in terms of the store itself, rather than just a little core plug. So it's important to upscale. So in conclusion, what I'd like to suggest is that there are many well design and construction challenges associated with the injection of CO2 for CCS. These wells present us with challenges. They vary depending on the condition, the initial conditions of the store. Is it saline aquifer or is it depleted hydrocarbon? And what exactly are we talking about? Do we have a potential to have heated supply of CO2, which would mitigate some of the temperature problems that we see in depleted stores? So there are a lot of questions and a lot of differences. And those challenges that we face, some of them are pretty similar to those that we faced in the oil and gas industry for years and years. There's no industry better placed to deal with these wells. We have lots of useful experience from decades of implementing oil and gas production and water injection wells. And most of these challenges can be addressed through study, through understanding, through laboratory testing, through modeling. We can actually understand these phenomena, even though some of them are quite complicated. The tests that we do, the modeling that we do, is actually quite similar to what we've done for a long time in the oil and gas industry. But we need to take into account that we're dealing in particular with a very special, very different type of fluid. CO2, as I said at the start, is challenging or interesting, depending on your point of view. So it does present us with some interesting challenges, but actually there are some really interesting and useful things about CO2 as well. Its viscosity, for example, when it's in dense phase, is very low. So its injectivity is vastly improved once we get into dense phase. So there are some really different and interesting things we need to understand. And so I would conclude by saying that CO2 storage wells and reservoirs are essentially the same, but they're different. So I'd like to say that I'm relatively new to carbon capture and storage wells, although I've worked on, it feels like many wells in the last 5 years. But my knowledge has been significantly enhanced by working with some experts in their fields. And one of those is Russ Gilbert, who was the low carbon team lead for the company I was with before I joined Elemental. And also Dr. Ross Anderson, who is a hydrate and salt precipitation guru, I think is the only way to describe him. And also I would like to acknowledge Dr. Rick Lemancic and Raymond Tibbles, who were my SPE Distinguished Lecturer Points of Contact. And what that means is mentor. I don't know why we have to use points of contact, but it's SPE terminology, so I'll use it. But essentially, they helped me through the process of putting together this presentation. So thank you to them. I'll come back to this slide if you have any questions or comments. I think we have a little bit of time for questions and comments, but I want to finish on a very important slide. Your feedback is really important. I can absolutely assure you that SPE pay attention to feedback that you give. It's what helps to, I hope, keep improving the Distinguished Lecturer program, and so please do give that feedback, whether it's positive feedback or, as we say in the politically correct word, constructive feedback. It's all very welcome. It doesn't go to me, so don't worry, but either do it through this QR code, or if you don't want or can't use the QR code at the moment, just go to the SPE website, go to Distinguished Lecture, and there's very clear route to give your feedback on recent Distinguished Lecture talks. So please do give it, and thank you very much for your attention.
Hello. Yeah, we have time for questions. Okay, I got the first one. Please let us know who you are and ask the questions.
Thank you very much. My name is Sasha. I work in exploration, and I'm like you to this. I'm new to the industry, Mike. So a couple of layman questions. So first of all, you talked about the limits of storage and about stopping injection. Like, is there a limit of storage of what a reservoir can take, and like what happens when that is reached? You mentioned vintage wells. So first of all, are they getting better the older they get because they're vintage? but like these vintage wells and like new wells you would drill, are they any different? And you talked about production wells and injection wells. So again, me, complete layman, can I not just use a former production well to now serve as an injection well? What's the difference? Could I also go and, you know, find a reservoir, an empty reservoir underground to, you know, use only for injection? Enlighten me.
So that felt
That
like
was a lot of stuff.
that was a lot of questions. Okay, so I think the first one was around the limits, and so all of these stores really will have limits. So in saline aquifers, it tends to be a pressure limit. So in other words, you can't just keep on injecting CO2 because there are some limits to what you may be able to tolerate in the cap rock or overburden. So you can't fracture out of the store.
So nothing more goes in, or
Yeah.
like just
No, it just gets abandoned, basically, yes. The same goes for the depleted hydrocarbons. So generally speaking, the plans are to fill these old reservoirs back up to their original pressure, but not to go beyond that, because on the basis that we reasonably understand that they've held that pressure for quite a long time, and they should be able to hold it again. One of the things that I didn't deal with, and it was deliberate, but it's also very important for these, from a storage point of view, are these vintage or legacy wells within the store complex, let's say, whether that's old wells in depleted hydrocarbon reservoirs, the exploration wells that have been abandoned. They are one of the biggest challenges of all. So what leaks could there be from those wells is one of the things that really puts a lot of pressure on operators to understand and assess. I was dealing with the injection wells rather than with those wells, which are a big issue in themselves. For the injection wells, yes, we can use some of those vintage or legacy wells. They don't get better with time. I just prefer the sound of the word. There's something more attractive about vintage, I think. But yes, they can be used. But yeah, I think we have to take into account that they weren't designed as CO2 injectors. They were designed as hydrocarbon producers, and they may not be tolerant of what we want to do in the CO2 injection phase. Potentially, yes, yeah. So, but there certainly are stores that I'm working on where we are using those legacy wells, and certainly some of the pilot wells and test wells that have been used to try to see if this is going to work in particular areas, they have been existing wells rather than new wells being drilled. Some new wells have been drilled, but often they're just wells that were there, and we take advantage that we're there. They're there to do some trials to see if what we're planning to do is actually going to work in wells, because we can have all the theory in the world, but the proof is very often when we try to really do it. Okay, I think that was most of your questions. Okay.
Yeah, good evening. My name's Andrew Kirk. I work for a power company called Byrne. Unfortunately, I'm a geologist as well, so the booze can start. My question and comment, actually. First comment is that from what I heard tonight, large reservoirs in large structural environments are better in terms of ease of injection, which means that somewhere like the Northwest Shelf of Australia, which I'll get onto in a minute, probably is a lot easier than to inject CO2 into some of the reservoirs in Thailand, just because of the size of the trap. With regards to, I have a business where we're wanting to inject 1.8 million tonnes per annum, which according to your numbers is about 100 million scuffs a day, roughly, on the Northwest Shelf of Australia. Dealing with the companies that are looking at creating commercial CO2 sequestration businesses, you see two sides. You see what happened at Barrow, and I'd really like your thoughts on Barrow, because I read many things and I still would like to hear somebody tell me exactly what the problems were at Barrow. Saline reservoir, naturally pressured. Then you look at what Santos is doing in Moomba, on onshore in South Australia, and the conversations I have with Santos, and I have quite a regular one, is that it's quite successful and they're making good money. So we're now seeing commercial outcomes which are being successful, well, according to Santos. I want to inject 1.8 million tonnes into the North West Shelf offshore. The business will be looking at that within 3 to 4 years. Most of the opportunities that have been presented to me have been depleted reservoir, which is what I would prefer just as a geologist on the basis of what I understand, which is not a lot. Your thoughts on the viability of the offshore of the North West Shelf of Australia, given what you know about the reservoir and the size of the structures, and also the comments between saline reservoir and depleted oilfield reservoir?
Yeah, and I don't. There isn't necessarily an easy answer, and it's something that's quite interesting in a way when you think about the nearest region to where I'm based is the North Sea, which, without offending anybody in the room, is mainly Norway and the UK. I was thinking of Denmark when I said that. But I think what's interesting about the CCS developments and development plans for the North Sea on the UK side is the majority are in depleted hydrocarbon. Some saline aquifer, but the majority are in depleted hydrocarbon. On the Norwegian side, exclusively saline aquifer. No depleted hydrocarbon developments so far. And I don't think it's because of the relative maturity of the reservoirs on either side. I don't know what the answer to that is. I've been trying to find out. I've been trying to understand what the now. And again, I don't think there's an easy answer to what is the best. You know, is it saline aquifers or is it depleted hydrocarbon? I share your view that the depleted hydrocarbon has a certain attraction to it because they are quite well understood. You know, we've understood them reasonably well to extract and to use them for their resources, and we know that they're good seals because that's why they've worked. I guess one of the disadvantages with the depleted hydrocarbons are these, let's call them legacy wells, because there are likely to be many penetrations that are with potentially variable records of how they've been abandoned, basically. Whereas on the saline aquifers may have very few penetrations over significant areas because they're not necessarily in hydrocarbon-rich territories. So there is that balance, and I can't give you the simple answer. But if you push me, I would say the depleted hydrocarbons seem more attractive to me.
I would comment that some, depending on the country, and I've worked in a few of them, if you have a good government system of core storage for wells that have, and fields, you actually have a database available to you to do studies before you actually start to decide what you're going to do. Whereas with natural saline reservoirs, as you say, limited penetrations, limited information, limited data, which in my case, my problem of course is that a lot of those fields are now 25, 30 years old, and God knows what the integrity of the wells and the associated equipment looks like. So
yeah, no, absolutely, and there's that balance. But and again, you make a very good point about core. I come from a core testing background, so I like core. I like when there's core available, and that definitely is an advantage for some of those depleted hydrocarbons. And also because they were developed in a time when people cut a lot of core, because you know that's why they're depleted, is because they were developed some time ago. I've been looking at one store. It's not actually in the North Sea; it's in the East Irish Sea, and the core coverage is just phenomenal. They've got multiple wells that are cored from the top to the bottom of the reservoir, and you just look at that as a geologist and you say, yeah, we pretty much understand this rock because we've got it all. Whereas there are some saline aquifers that are being developed with no core.
yeah, and the cap pressure work that's been done on the seals as well.
Yeah.
That is fundamental as far as I'm concerned.
Yeah.
Is understanding.
But you know, there are some of these saline aquifers. it's probably no big secret, but I won't give the name anyway, but there's one of them of Australia that they've cored recently, and they have cored extensively in the cap rock. And it's a saline aquifer, and in the store itself, but in the cap rock they've cored extensively so that they can understand it, basically, so that they can understand if it's going to be a legitimate seal for thousands of years. And that's a good thing, you know, that they've gone to that effort.
Actually, in a sense of time, I'm sure Kun Mike, not Michael, will still going to be here after the meeting, so you can continue to engage. And on behalf of SPE Thailand, can I have Kun Surachai, one of our SPE program chair, to provide the token of appreciation for our speaker this evening.
Do you need to come up here? Let me get it.
All right. So thank you very much, Mr. Byrne, for his wonderful presentation. To share with you the upcoming meetings, next month we have topics very close to our heart, and is related to Gulf of Thailand drilling and its evolution to what we today taken for granted. So Kun Pasuk, who many of you have known very well, one of the drilling legacy in Gulf of Thailand, will deliver this talk from his personal experience. And in December, we will have a break for Merry Christmas. And I believe some of you may join the TOCI golf event. So SPE Thailand will return in January 2026. So we all hope to see many of you there. And also our neighbor section, the SPWLA Bangkok chapter, is organizing their meetings the week after ours, coincidentally along the same topic of CO2 related, but more on the geological standpoint. If you are interested, please check out their website and also consider joining their meeting as well. And in addition, you may also check out the SPE Asia Pacific upcoming events, which will be held within our region. Right, and there are several ways to get in touch with us. You can check out at our website, connect.spe.com/Thailand. And you can also follow and like us on new Facebook at SPE Thailand Facebook page. Everyone's scanning. And look us up on new LinkedIn and join the SPE Thailand section group. We also have a Line, if you use Line, official account, where you can follow our upcoming events, register or even apply or renew your membership. Just scan any of these QR code shown here, and it should direct you to there. Okay. So SPE Thailand, once again, I have a YouTube channel where you can look at our recordings from later viewing. And please check this out, SPE Thailand YouTube. And finally, the lucky draw. Can we please have our speaker, Ms. Byrne, to the front and help us with drawing two winners?
One at a time.
Lucky draw is a shirt.
So I throw this now?
Yeah, throw away the first one. You want to announce?
I'll try. This one should be okay. So it's Sasha Honoryu. Oh. I could pronounce that. Well done.
Change your shirt, okay?
I hope it's gonna fit me. I hope it's gonna fit. Oh wow, Cassian, your lights blinding.
I should fit you, Sasha. Yeah. I got a small shirt here, but that one fits you.
Is it small Asian or small Western size?
That's your size.
Oh, so I was really afraid that some of these names I wouldn't be able to pronounce, but this one I can do. It's Ben from VE.
Don't tell him. Sorry, Ben, that shirt won't fit you. Give it to a student. You can sail it.
All right. So last but not least, please give a big round of applause for our sponsors. Right. And that concludes our program for this evening and this night. So on behalf of SPE Thailand, I would like to say thank you for attending and wish you all a very good night. Thank you.
Of course, as usual, we do have the 2-for-1, whatever special drinks by the hotel at the Kuku Bar downstairs. If you want to continue, just say the password SPE and you'll get the 2-for-1. Thank you.
Thank you very much.